Hi everybody, Physics Ninja here. Today what I want to do is look at transverse waves again. I'm going to consider a transverse wave that's described in terms of one harmonic here. So the amplitude at any position x and at time t is given by a simple harmonic function like this, either a sine or a cos. And my goal is to calculate what is the average energy in one wavelength, for example. I also want to look at the average power. Okay, so that's the rate at which energy is needed in order to create a wave like this, or how much energy passes a particular point if one wavelength goes by. So two important concepts when dealing with transverse waves. We're going to see that the energy is broken down in terms of kinetic energy of every little segment of rope, because every segment moves up and down in the transverse motion, so it has kinetic energy. And we've also started off with just a straight rope, and then we've bent it, right? We've made the rope basically longer by doing work on it. When you do work, it also means you have stored some potential energy in that string. In this case, it's in the form of elastic potential energy. So we're going to use both of those concepts to calculate the average energy. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, so a couple important aspects about this transverse wave here. So we have a formula for our displacement in the transverse direction. That's in the y direction right here. This wave is traveling at a speed v. Again, the speed is related to the frequency and the wavelength like this, or you can write it in terms of the angular frequency and our wave number like this. Okay, so that's the speed of propagation of that wave. What other characteristics do we have? The tension in the rope is going to be T. Okay, I'm just going to use, actually what we're going to do is just not to mix it up with the period of oscillation. I'm going to call it the tension as force sub T. Okay, so this will be a force measured in newtons. Okay, what else? The rope has a certain thickness. It's characterized with a density. Okay, so this is what we call the linear mass density. The amount of mass you have per unit length of this string. All right, so I'll just call this mass density. And from my previous videos on waves, we talked about how the speed of propagation is related to both of those parameters through this expression right here. All right, so remember that this y displacement here, if I take any little bit of rope at some position x, each segment of rope simply moves up and down. Okay, that describes the y displacement. And every little segment of rope has a little bit of length, and it has a bit of mass, right? It has a small mass dm. Therefore, if you have a little bit of mass that is moving up and down, you have to have some kinetic energy. All right. We're also going to see that the rope is actually stretched a little bit because we do work on it. So that's going to introduce this concept of elastic potential energy. Okay, but to get started, we're first going to focus on calculating what is the average kinetic energy in one wavelength of a transverse wave. All right, this will be the first thing we consider, and then we'll look at the elastic energy stored, and then we'll simply add both of those up to get the total mechanical energy of this wave. All right, first thing we're going to do is look at the kinetic energy of in transverse waves. So I have the displacement as a function of time is given by this. And you may have remembered from physics class way long ago that kinetic energy was given by 1/2 mv squared. Well, how do you apply this to a transverse wave? Right, it's a good question. So what we're first going to do is we're going to need the velocity, okay, of every segment, because we need the v squared term over here. So how do you get the velocity? Well, if I gave you a function for the displacement, the y component of that velocity, again, it depends on position and time. What you have to do is simply differentiate this function with respect to time. So if you do that, again, you're just taking the derivative of a cosine function. So that becomes minus a sine of everything that's the same here in the argument. And then you have to take the derivative with respect to time of this thing, right? So if when you do that, there's another omega t that comes in. That's just using the chain rule. Now we're going to group together some of those terms. See, these negative signs are going to cancel out. So here you're left with a omega sine of kx minus omega t. All right, so that is the instantaneous velocity, the instantaneous position of this transverse wave. So let's go back and look at Let's look at a tiny segment. So a tiny segment of the rope is going to have a little bit of kinetic energy. I'll call it dk. I still have the 1/2 term, which is here. Now for the mass, what I'm going to do now is substitute, well, it has a little bit of mass, call it dm. Okay, and now what I want to do is substitute that vertical y and make that term squared. All right, what we're going to do now is we're going to take a snapshot of this wave, and I'm going to call this, for example, at time 0. Okay, it doesn't matter at which time you do it, it simply will shift this wave to the right if I look at a later time. But at time 0, let's just assume that this is a snapshot of the wave. So at time 0, what we have is we have a position, which is, see this second term here with omega t is going to go away if I consider at time 0. So let's just take this, a snapshot at t equals to 0. Okay, so the way you do this now is the little bit of kinetic energy of the segment is 1/2. Instead of writing dm, I'm going to use my definition of mass density. I'll substitute dm for this mass density multiplied by the length here, dx. That's the definition. And now I'm looking for that velocity in the y direction at time 0, and I have to square that value. So you're basically just substituting time equals to 0 in here. So you get a omega sine of kx, and then I have to square this entire thing. All right, what I'm going to do now is I'm going to bring the dx down at the bottom over here. So what this is the energy you have per unit length of string. Okay, so here is going to be 1/2. I have the mu factor, which is there. I'm going to have now, if I evaluate this square term, you have a squared, omega squared, and now this becomes sine squared of kx. All right, this first equation here is the kinetic energy density, or the kinetic energy you have per unit length of that string. All right, so this is our kinetic energy density. Now what we really want to do here is you want to find the kinetic energy, for example, in one wavelength. So what would you have to do? Well, you would have to add up all of these small little bits of kinetic energy and integrate them all over one complete wavelength. Okay, well, let's go ahead and do that. So what you have to do here is substitute dk in this expression. And dk is simply bring dx on the other side. So this is all we have. You have to evaluate this integral here. We have 1/2 mu a squared omega squared sine squared kx dx. Now what you do to simplify your life here is you bring all the constant terms out in the front of the integral. So that's the 1/2, that's the mu, that's the amplitude square. This is the omega squared term. And then you're simply left with something that's more manageable. So sine squared kx dx. Now what you could do is use some trigonometric identities. One of them I like is sine squared. You can write it as, in terms of a double angle, as 1/2 minus 1/2 cos of 2 times whatever angle you had. So that kind of helps you evaluate this integral without resorting to tables. Okay, so let's go ahead and do that. So again, I'm just left with this expression right here. We're going to rewrite it, 1/2 mu a squared omega squared integral from 0 to 1 wavelength. And instead of writing sine squared of kx, all you end up doing now is substituting that sine squared using our double angle formula. All right, so here you get 1/2 minus 1/2 cosine of, again, now it's going to be 2 times kx and evaluated over, multiplied by dx. All right, now this is a pretty straightforward integral to evaluate. All right, there's 2 terms, so you have to be a little bit careful. Go ahead and do that. So you get 1/2 mu a squared omega squared. The first term is pretty straightforward. First term, all you get here is x over 2 and evaluated between both of those limits. And our second term now is going to be minus 1/2. The integral of cosine is sine, and you have to divide through by 1 over 2k, and this becomes sine of 2kx, again evaluated between both of those limits. Now this second term looks rather complicated, but you have to remember our definition of k is 2 pi over lambda. So actually this second term here, you could see when you substitute lambda in here, the arguments here are both going to give you sine of something that's going to give you 0. So you don't really have to worry about this second term right here. You're only going to be left with our first term. So that means that the kinetic energy in one wavelength, they're kind of like our average kinetic energy right here, is 1/2. Again, I'll just do one more step here. A squared omega squared. And this term here simply becomes lambda over 2. What we can do is just group all the numbers in the front. So you get 1/4 mu squared, omega squared, lambda, and a squared. Okay, so this is my final expression. Not too bad. What you can also do here, and sometimes you can write this in various forms, because you also have my expression that the speed is equal to the frequency multiplied by the wavelength. So again, if you want the wavelength in there, sometimes you can write this expression slightly differently, but the key parameter is really the a squared parameter, right? The average kinetic energy is proportional to the amplitude squared. Okay, so that's a really important factor. All right, let's now go look at the elastic energy in one wavelength, and then we can add it up to this value in order to get the total energy per wavelength. All right, we now want to look at the elastic energy in transverse waves, and what I want to do here is look at that little segment of the mass again, a little segment of string. Now, before there was a wave, well, that little segment of mass had a mass m, and it had a length dx. Now, when there's a wave, first of all, it's at an angle now, right? So it's kind of tilted like this. The mass of that little segment is still the same, dm, but look what happens to the length. I'm going to call it ds here, some small length. The length has changed now, okay? It has changed because there was a tension force, right? Somebody wiggled their hand up and down and made the rope basically a little bit longer. There was work done to stretch that little bit of string. And if there's work done, that is energy stored in the terms of elastic potential energy. Okay, so what we're interested in now is let's zoom in on that little segment right here. And I'm going to call this ds. I'm going to call this length here dx. This is what I started with. And now it has some slope to it. Okay, well, what you can do now is you could just use Pythagorean. You can write ds in terms of those other lengths, dy squared. And what I'm interested in now is, well, let's factor out a dx from this square root term. So if I do that, I'm still going to have a square root. Here I'm going to have 1 plus, I factored out a dx. So it should look something like this. All right, now what we want to do is we're going to assume that if dy over dx is small, right? If it's much less than 1, there is something called Taylor expansion that you can do, or binomial expansion here. For example, if you have a term like this, and if x is small, what you can do is you can approximate this as being 1 plus 1/2 x. And then there's higher order terms, but I'm going to ignore those if x is small. So if I apply that to this little bit of segment over here, what you can do is write ds as being dx. And now I use the expansion for the square root term. So it's going to be 1 plus 1/2. And now it's dy over dx squared. And then plus some higher order terms, which are much smaller. Okay. All right, so let's have a look at both of those terms. Now I'm just going to multiply through by the dx. So what you have here is dx and then plus 1/2 dy over dx squared multiplied by dx. All right, this is the approximate length, my expression for this new length. Now look what we have. The first term is basically this initial length. That's the initial length we had right here. So this other term is how much it was stretched by, right? That is the little bit of extra length that we have when there is a segment that's at an angle like this, okay? So what we want to do now is if we stretch the rope by this much using a tension force, that's the force present here in the string system, how much work was done in order to stretch it this amount. So let's now go on the next page and calculate that. All right, we're now interested in calculating the quantity, the elastic energy now, or the total amount of work that's done to create one full wavelength. So again, the work formula is a force multiplied by a distance or a change in length, right? Displacement. So what you have here, the force that is stretching, the force that's uniform inside the string is the tension force. The change in length is dl. It is that second term here that we evaluated. This is how much the string elongated. So you simply have to bring those together. And what you now want to do to get the total potential energy in one wavelength is we have to integrate the total work, right? We want to integrate over one wavelength. We want to integrate this expression, Ft 1/2 dy dx squared dx. Okay, so this is what we're left with now. So what we're going to do again is bring some of the constant terms in the front. So this is Ft divided by 2. That's straightforward. And now we're left with this integral. Now we're going to have to simplify this dy over dx squared term. Okay, and for that we're going to go back to our displacement. Remember, my displacement was given by a cos of kx. Again, I'm taking a snapshot here at time equals to 0. So you have to take the derivative with respect to x, and then you have to square that term. So this is dy with respect to x. Again, it's minus ka sine of kx. All right, we can square that term and substitute it into this expression. And then it's going to eventually give us what we're looking for. So Ft over 2, integrate 0 to 1 wavelength. Now we want to square this term. So it's minus Ka sine of Kx dx. And don't forget to square everything. Now when you square, it'll take care of this negative sign. Then you can bring out other factors to the front of the integral in order to simplify it. So this is Ft over 2. This is K squared. Aha, A squared, that's the amplitude squared again. And here we're left with a similar integral for what we had for kinetic energy. This is sine squared of kx dx. Well, guess what? We already evaluated this term in the previous problem, right? This is the same as before. And this guy here reduced to simply lambda over 2. That was the answer, right? There is no difference. So you just follow the exact same steps. All right, let's go on the next page and finish this off. So finish off our calculation for potential energy. And at the end, we're interested in the total energy. So we need to add the kinetic energy to this. All right, these expressions look similar. This is what we had for elastic potential energy and for kinetic energy. Now they use different terms. This potential energy has the tension force. The kinetic energy has the mass density. But you have to remember that both of those are kind of linked together here. We had an expression for the speed of the wave. And the speed of the wave you can write as omega over k. If you square both of these terms, what you get is Ft, tension force over that mass density, is omega squared over k squared. So guess what? You can write that tension force in terms of omega squared over k squared multiplied by that mass density. If you do that for this term, well, look what happens. So instead of writing Ft here, we write omega squared divided by k squared multiplied by mu. Then you still have the other terms. You still have another k squared here. You have a lambda. And you have an amplitude squared. Now there's so many terms here. That's okay. The k squareds cancel out. And now, well, look what you have. You have the exact same expression, right? The average potential energy, or elastic potential energy, and the average kinetic energy in one wavelength here are the exact same thing. So guess what that means? That means that our total energy, again, we're looking at per wavelength here. You simply add both of those up. A quarter plus a quarter gives me 1/2. And this is mu omega squared lambda a squared. I think the key to this equation right here is just realizing that it is proportional to the amplitude squared. Okay, so that's really, really important, that the energy in a wave is proportional to the energy squared. All right, now I want to look at the energy transmitted, okay, or the rate at which energy is transferred when a wave travels past a particular point. Okay, and for that we're going to look at the power, right? What is the power transmitted? All right, and now I just want to say a few things about power. Okay, we're looking at power transmitted. The definition of power, again, is just the rate at which energy gets transferred, right? It's energy transfer per unit time. Again, this is for a sinusoidal wave that we're looking at on a string. So if I try to write it as an equation, well, my power is, well, what is the energy, change in energy per unit time, right? That goes by a specific point. Now we calculated how much energy there was in one of these wavelengths right here, right? And if this wave here travels to the right at some speed v, well, let's imagine how much energy goes by a specific point when a whole wavelength passes this point x. Well, what we would have in that case, and this is kind of like an average power, okay? The change in energy that would go by, well, it would simply be my total energy of that wave, right? This would be 1/2 mu omega squared lambda a squared. Now, how much time does it take for one wavelength to go by this point x? Well, this is very, very straightforward, right? The speed is just the distance that it travels divided by the time that it takes to travel that specific distance. Well, guess what? Then you can write the time as the wavelength divided by the speed. All right, so the amount of time here that it takes is simply lambda divided by v. Notice you have a lambda in the numerator, 1 in the denominator. Now I can bring this v upstairs and you get an expression for my average power. Now it includes some of the same terms, but it also has this speed here, okay? The speed of the wave. All right, so this is the rate at which energy gets transferred as the wave passes a point x right there. Now we could derive this a little bit differently by looking at work, but this is kind of the easiest approach, okay, in order to calculate power, especially since we've done all this work to calculate the average energy in one wavelength. All right, that's it for this video. Thanks for watching, folks. So again, the key, total energy and average power, both depend on the amplitude squared.